Okay, we might as well get started. Welcome. So the midterm is over. I hope everybody did all right. I'll have a couple comments about that. And then Stanford Shell, I hope that's going okay. As I said, there's if you haven't really gotten going on it, get going soon. It's for those of you who have started it, you realize there's just lots of parts to it and lots of things to think about. And there have been lots of Piazza questions, good Piazza questions about the assignment. So I hope that's going all right, and we will have lots of office hours this week. And when did I say it was due? Wednesday night or Thursday? Wednesday night. Okay. Did you say make it Thursday night? Is that what you said? Let's talk in a couple days. We'll see. So the midterm, a couple comments on that. You should have gotten your midterm scores back. If you didn't, please let me know so we can make sure that happens. Overall, I was pretty pleased with it. I think there were a couple questions on there that I knew would be difficult, and there were a couple questions that I thought, hey, everybody should do all right on this, and most people did. The answers to the file system stuff, I think that was hopefully relatively open-ended but straightforward. Most people did okay. Problem 1D, actually problem 1 I think was the most challenging problem, which it was kind of meant to be. 1D, let's go kind of in reverse order here. 1D was the question about, hey, how do you de-interleave these outputs? Is it possible to really de-interleave these outputs? The answer is not really. The way we set up the input and output such that they had to track each other directly made it really impossible no matter what solution you came up with, unless you were allowed to collect all the data first and then pipe it to one, then pipe it to the other, and so forth. And the idea for this problem was you don't know how much data there is coming in, and you're not allowed to store it all before you start piping it away, and it's not possible. Very few people got that part correct for D, but that's okay. That happens on exams. Definitely go and look at it. If you do have questions about, hey, I don't really understand what the answer is all about, trust me, we had some TAs during grading who were like scratching their heads going, oh, wait a minute, what is this? And they did it all on the board, and they convinced themselves eventually. So it was a difficult problem. For the actual code for that, two things. First thing, you know how we can use the pipe 2, and then you have like FDS, and then EXEC or whatever it is. You know how to do that, and then you don't have to close some, but you might have to close others and whatever. We didn't even worry about that, all right, for the exam. There were too many corner cases where you could have done one or the other, and we just pretended everybody used that pipe 2, and we pretended that everyone closed everything inside the children correctly. There were 2 pipes you had to close correctly, or 2 file descriptors you had to close correctly outside of the children, and that one we cared about. But inside the children, if you said, oh, I'm not sure I got that right, that's okay. We didn't worry about that. The other thing that people tended to miss quite frequently was we didn't say you should wait PID for the children to end the program. But let's just go look at the program, the actual question again, okay? Or I should say, let's look at the actual code that you may or may not have typed up. Hang on, remind me later. Cursor, there we go, and then there we go. Vim to output.cc. Okay, so you wrote all this for the actual pipes and so forth, and you did all that, and you were writing where? You were writing in main, right? You were writing the actual main part of this program, which called the dual echo down here, okay? Which called the dual echo down here, and that was what you did, and then main ended, and if you forgot the wait PID, this is what it should have looked like, by the way. Let's see, to output, let's do the same example to do sort, and then I'll pipe in a little test input. Okay, so that was actually relatively nice in that it did sort and WC, and the word count actually did come first, but it didn't have to. It could have come somewhere in the middle. That was the interleaving part. But you'll notice that the prompt didn't come back until after both children finished. That's what you want in programs. You want your programs to end nicely such that the prompt comes back. Well, if we took out those 2 wait PIDs, right? let's see what might happen. Okay, it's not guaranteed to happen, but let's see what happens here. Output, oops, output, there we go. To output, and let's do the same thing before. Let's do it up at the top of the screen. There we go. Okay, look. So here's what happened. Up here, we got the prompt back, and then the program went, and then it just sits here like that. Is that a nicely behaved program? No, not very nice. So we kind of expected you to go, oh, if I'm writing the main and I'm doing this to output thing for children, you should wait for the children. So I apologize to people who didn't pick that up, but you kind of should get that's what you want to do. All right. If you have there are regrade requests still open. We're relatively strict about regrade requests in that you can't, like, for the pro and con one, you go, well, I really meant this, and try to explain away what you really meant. And if it wasn't on the page, that's it. The other one, there were some people who were saying, I wrote 125 words and you took off points and whatever. I kind of warned you that the point we thought those answers could be well within 100 words. And so if you made a few more, we didn't care that much. And if you do want a regrade request, I'll go count your words and make a decision. But like 120 is probably too much in that case. Question?
I just had a question about pipes filling up. Is that based on our implementation of write, or can in general pipes?
Good question. The question is, hey, wait a minute, I didn't know about this pipe filling up business. Is that the way write works, or is that the pipe thing? It actually is a pipe. It's a built-in Linux issue, is that pipes can fill up. They only make so much space for the pipe in Linux. And so all it does, it generally doesn't break things. Although if you don't understand that, like this code, it would break our code if we tried to de-interleave, because we never really talked about that. No, we didn't talk about that in the sense, like, there might have been a Piazza question about it. Maybe it was last quarter, but the point is that the pipes can fill up, but what do? They just block until things lessen up again. And if for some reason you're doing something wonky like that program and trying to collect all the data at once, that can be a problem. So that's kind of why I gave it on the exam was, hey, here's something new. Oh, what do you think about this? Oh, now that pipes can fill up, what do you think about it? That's kind of why I put it on there. You see what I mean?
Not the part where we knew that pipes could fill up.
No, you didn't know that pipes could fill up. No, what I'm saying is you might have known that, but.
Did it say that on the exam?
The midterm said it. Oh, yeah. There was a section. Oh, sorry. Yeah, sorry. Go back and read the midterm. It did say, and that was the whole point of, the pipes can fill up. Sorry, you didn't read that. Question?
When the pipes fill up, does it close the file, or does it, like...
No, good question. When the pipes fill up, does it close the file? No, it just blocks on it and says, oh, if you want to write more data, I can't accept more data. I'm just going to block you from writing more data until somebody else reads. And then you'll be able to undo it. We're going to see an example of something similar to that in threading today, where there's this reader-writer kind of dance that has to happen where you've only got so much space and you need to figure that part out. So good question on that. Very good question. Yeah. A little more technical question about main, yes.
So in my code, I used a for loop with the weight PID, the PID being -1, no 0, and I had a for loop.
You had a for loop kind of around this within weight. Okay, that probably could work, sure.
It still says that I didn't get credit for that.
Oh, I'll put a regrade request in if you think that's right. Doing the weight PID in a loop where you check for all the children waiting is perfectly legitimate. You absolutely could do that. So put a regrade request in for that. Yeah. Any other questions on I don't want to get into too many details about the exam, but if you do think we graded it incorrectly, please let us know. As I said, we're trying to be fair in the regrade process, but we're going to be, we're going to be not going to just let you kind of redo your test in the regrade process. You've been through that before. Okay. All right. As I said, overall, pretty good on the midterm. I think it was a challenging midterm. But overall, people did all right. And if you didn't do so great, feel free to email me and we can chat about going forward and trying to pick things up a little. And you've also got final and other assignments and so forth. Okay. All right. Now, so I know you're all thinking about Stanford Shell, which has nothing to do with threading, but I did figure that last week you were all thinking, oh my gosh, I got this midterm coming up, and we went over we went over mutexes and then CVs and semaphores, and it was all wicked fast. And what I wanted to do is kind of go back and just kind of review what they are, let you get all the questions out that you might still have about those, or new questions, or whatever. And then we'll see a couple more small examples. Okay? I'm not going to actually do any live stuff today. I'll just have some examples and we'll go over them as we go. Okay, so in threading, we have to have this ability to handle race conditions. We have to have the ability for 2 or more threads to either act in a similar section of code or act on a data structure in a way that won't corrupt the data structure. And this is just something that you have to deal with. Race conditions happen all the time when you're doing this, threads, just like multiprocessing. We have a few different ways of doing that. We kind of walked through them last week. The main one is, and this is the kind of the underlying one for most of these, is a mutex. Okay, a mutex, and we'll go over the details. I'll just kind of list the 3 here. The mutex is the first one we learned about, and we'll see examples of that in a minute. A condition variable any. Mutex has no ability for 2 threads to signal another thread that they're done. Right? Now, the signaling can happen by the fact that one thread will actually release the lock and the other thread will gain the lock. So that is in some sense a signal, but it's not a distinct hey, anybody who's waiting, go ahead and continue. So there has to be some ability to do that if you don't want to busy wait or if you don't want to just have a regular straight up lock. Okay, this is particularly important when you have multiple things trying to access a particular particular section of code, and it could be more than one. You can't really handle that directly with a mutex. So that's where condition variable any comes in. And then there are all sorts of things you can do with a conditional variable any that we happen to do a lot, namely waiting for permits and saying, hey, here's a whole bunch of a whole bunch of permits that a bunch of threads can work at once. And so what we said was, well, we can use a condition variable any, but let's actually build it up such that we build it into this other thing called a semaphore, which is a different type of data structure, fairly easy to build, has some nuances that we'll talk about later today, and it allows you to go ahead and build more structures a little easier than a condition variable any. Okay, so let's review these. Okay, let's review all of them. In fact, let's see. There we go. Maybe not. Hang on. Oh, there we go. Okay, so the mutex. Okay, and you can use these slides as kind of a reference too, if you'd like. The mutex is it's a lock. Okay, and it has 2 things you can do with it. You can say either lock or unlock. And what happens is when a thread takes this mutex and locks it, if no one else has locked it yet, it gets that and it moves on to the next line of code. Okay, and it's that straightforward. If another thread comes in and attempts to use the lock, but the first thread is still using it, then what happens is the second thread blocks until the other thread unlocks it. Okay, and that's the big details there that you should care about. Okay, you have to pass a mutex by reference or by pointer. Why? Because they actually need to share the same mutex. It can't be a copy of a mutex because then the data wouldn't be shared. And that's how it works. And by the way, under the hood, if you take a parallel processing class or you take maybe an operating systems class, they might talk about it uses atomic instructions under the hood to create the mutex so that 2 threads can't get it at the same time. So there's a little more hardware support and operating system support for doing this. But that's basically how it works. Okay, the thread obtains the lock and then executes the next line of code. If the other thread can't get it because the lock is already taken, the code waits and then until the lock is unlocked. The only thread allowed to unlock is the one that locked it. Okay, it's undefined behavior if another thread tries to unlock a locked thread and it wasn't the one that did it. Yeah, question.
Wait, hold on.
Good. I'm listening. I'm trying to get this tablet thing working. Yeah.
I don't remember.
You don't remember your question? Oh, okay.
It disappeared.
What's that?
It disappeared.
Okay. All right. So let's see. I'm going to try this one more time with the tablet and see if it
Oh,
works.
wait, I remember.
Go ahead. What's your question?
Locking for the lock, is that busy waiting or is that like okay waiting?
That is okay waiting. Okay, good question. The question was, hey, wait, is that busy waiting or is it okay waiting? That is okay waiting, but it doesn't always solve all of our problems, right? So the permits part, you can't really do that with one mutex, or even just a few mutexes, because as we saw with the traveling philosopher, I'm mixing my big problems in the world with the dining philosophers. You have to have the ability to say, oh, I'm limiting it to so many people being able to do this, so many threads doing something with that. So you have to wait on that. Okay, all right. So, other question? Yes, Eva.
What does mutex look like in terms of file descriptors? So threads share the same file descriptors and the same memory. Is that where's the lock happening in place? Is that like pointers?
It's an interesting question. The question is, what is going on with when there's locks and file descriptors? Remember, a lock has no information about the rest of the system. Okay? If two threads happen to be working on the same file descriptor, if one thread reads a bit, the other thread will read later in the file descriptor. But there's they could read at the same time, and it would just interleave it as is necessary. But yeah, if you want to read only apart from one thread and then something from another thread, having a mutex is perfectly fine, and you can order it that way if you want to. But yeah, there's no other reason. Remember, mutexes are relatively simple. You either hold the lock or you don't, and any other thread that tries to get the lock can't while you're holding it. That's the whole business with a mutex. Okay. All right. Let's move on to let's see. A couple other things about it. Oh, you should try to hold a mutex for as short a time as possible. Okay, why? Because if other threads are trying to access that lock and you're still holding it because you're doing something else, if it doesn't matter to your logic that the lock is still held, release it earlier. Sometimes it's inevitable and you have to release it, later on because you're still using that data structure, but you want to really hold them for as short a time as possible. Okay, let's see. Deadlock, which is when two threads are kind of waiting on each other, that's not really possible with a single mutex, because either one lock or one thread has it or not. It's not like they both can have it. If you have multiple mutexes, that's when we start getting into the deadlock problem, which is why we have to go on to figure out other ways of doing this. Okay, so one very nice helper class that's the easiest class in the entire world is this thing called a lock guard. And a lock guard is as simple as this. It has two methods, a constructor and a destructor. The constructor locks the lock, the destructor unlocks the lock, and that's it. There are no other functions, no other variables, nothing. Okay, it just either locks it or unlocks it, and that's it. It takes a mutex as its parameter, so I guess that's the one variable it may hold as a reference to the mutex. And what it's nice for is if you know that you are going to use a lock and then leave a function or leave a while the whole function, you might as well put a lock guard around it so you don't have to remember to unlock before you leave. It'll happen automatically for you. And it's nice in cases where you have conditional behavior where maybe you're inside some while loop and you return from that while loop. Great, the lock gets unlocked for you. You don't have to remember to do it. Or if you break out of the while loop and then leave the function, the mutex will get unlocked for you as well. So it's a very nice convenience class to use if you know that you have to do that. Sometimes you can't get away from it because you do need to unlock. And again, don't put a lock guard at the top of your function just because it's nice to use if you know that there's other things you're going to be doing in that function that other threads might want that lock. That would be a bad use of it. Okay, but you'll see more examples of doing this. Okay, all right, that's a lock guard. Now, a conditional variable any. This is the one that's a little trickier to understand. Let's review what it does. Okay, it works in conjunction with a mutex. So you have a mutex, and then a conditional variable any has the ability to wait for a signal based on that mutex. Okay, so basically what it does is it takes the mutex and you lock the mutex, and then you do a wait on that mutex, which is this conditional variable any that uses the mutex. the conditional variable any will push you off the processor because you're waiting for something to happen, and then it will unlock the lock. So it's very similar to sig suspend in that case. Okay, you can think of it as analogous to that. But the user should always lock the mutex first. Then you're generally going to check some condition. Okay, and you are going to, if the condition is met, you are going to go on to the next bit of code. So this is where conditional variable any could be a little bit like easier to use. We will make it easier to use in a minute. Okay, and when you get this notification, the wait function tries to reacquire that lock. It may not be possible because two threads are waiting, and if they both get a signal at the same time, which often happens when we do conditional variable any notify all, CV notify all, when those two get that signal at the same time, they race to acquire the lock. One of them gets it, the other one just continues waiting. Okay, so that's the deal with conditional variable any's and their ability to do that. And when the wait comes out of the wait, that you now have the lock again. So when you get a signal, once you get the wait, then you actually acquire the lock again. So you should unlock it later. Okay, that's how the conditional variable any works. We use this often to do permitting, where you say I have these X number of permits, and I have those number of Y number of threads, which is more than X, trying to access this, and I say only that many can do it. Okay, and the general idea is you're going to have something you're waiting on, the permits in this case, while it's equal to 0, you're going to just keep waiting. And the other function will say increment the number of permits and then notify everybody. Okay, that's how, and then that's when you would check, you would try to acquire the lock, you acquired the lock, you'd recheck the permits, see that it's 1, go out of the thing, and then you would decrement the permits because now you're holding 1. So the conditional variable any, if you understand it, you go, oh, I see what's going on here. There's lots of nuance to say, or lots of incrementing and decrementing, because you're trying to keep track of this one variable, which is a permits type variable. Okay, so that's what you have to do. That's what the conditional variable any does. Because of this wait being because of this while loop being really common, well, they built into a conditional variable any the wait into another type, or they built that while loop into a second version of wait, which works like this. It takes the mutex, just like the regular conditional variable any wait, and then it takes a predicate, which means a function that returns true or false. Okay, that's the while condition, and it actually does it in the opposite way, which is, you can read it like this. Okay, and this is important. If you read it, it basically, this down here, and often we make that function into a lambda function because we can. Otherwise, we'd have to call it as a separate function, which sometimes is a little awkward. But in this case, we just do it as a lambda function. We say, like in this case, CV wait on the mutex m, we pass in the number of permits so that we can access it. This is in the capture clause. And then we say return permits greater than 0. So you can say wait until permits is greater than 0. That's basically what this is saying. Okay, I like to use that like until in this case. Wait until permits is greater than 0, because it's really while not permits is greater than 0, keep waiting. That's kind of what it really is. But in this case, I just think of it as like, okay, well, when permits becomes greater than 0, that's when I can exit this wait. Okay, that's what we're looking for, the until part of that. Okay, so that's how conditional variable any's work. You will see those in lab this week. And you'll practice using those a bit in lab. Okay, but again, you still have to, with using these conditional variable any's, you still have to do the things like keep track of the permits directly yourself. Okay, and that's maybe or maybe not what you want to do. If you don't want to do that, well, we have another way. Okay, the next thing we're going to look at is the semaphore class. So a semaphore is also relatively low level, although for whatever reason, it's not built into C++ for us. Okay, why? Could be because it's actually really easy to build. We'll take a look at the code again in a second. But second of all, once we build it, we can use it, and we will allow you to use it for the rest of the assignments. We've already built it for you, and I'll show you that. But here's how it works. It takes away all of that increment and decrement the permits and does it for you, which is very nice. Okay, it's really easy to set up a semaphore. Okay, you basically say semaphore permits 5, and that says there are 5 permits. Okay, and if you do permits.wait, what it does is it looks and goes, oh, how many of the 5 have been used? Oh, none of them? Okay, you get one. And it gives you one, and then it decrements the permits. Now 4 are available. All the way down to 0. When there are 0 available, it just waits. Okay, and then when you say permits.signal, that is you giving up the permit, telling anyone else waiting for the permit waiting for the semaphore, I have released one, go fight for the one I just released. Okay, and the only time that actually signal gets sent is when you go from 0 to 1, because that's the only time it matters. Otherwise, it will always be able to get the permit. Okay, so that's how that works. You can think of a mutex as a special case of a semaphore with 1 permit. Kind of, okay? You shouldn't, in fact, if you go look at this up on like Stack Overflow, there's lots of people saying, don't think of it that way, that's not a good way. It's not exactly the same. Some people have said, oh, this is exactly the same. It's not really, but you can think of it as being with 1 permit, except that now you can actually do a signal when you're done with it. And the interesting thing about a semaphore is you can signal from, well, you don't have to be the one acquiring the lock to signal. Like, that's the big difference there. In a mutex, the only thread that can unlock the mutex is the one that locked it. That's kind of the other difference there. Okay. Now, a couple things we didn't talk about semaphores. What would a semaphore initialized with 0 mean? What do you guys think? If I did a semaphore initialized to 1, it would mean there's 1 permit, and if I have 2 threads fighting for it, and they both try to get it, one will get it, then when that one signals, the other one will get it. What would a semaphore with permits of 0 mean? What do you think, Hasna?
Would it just hang because nobody's able to get and turn it to lock?
Well, so it's a good question. The question is, would it just hang? They would, if you had 2 threads trying to get there, they would both wait until what? What do you think?
Is it like only the parent of the threads can access this data?
Only the parent can access the data? Not quite. You're on the right track. Somebody else has to do something. What do we say locks for mutex? The only thing that can release the mutex is to unlock it is the one that locked it. Is that true for semaphores? No, anybody can signal on a semaphore, right? So you're getting there. Anybody else want to take a stab at what this actually means? This is actually an interesting case. Yeah, go ahead, Eva.
You're waiting for someone to signal so that it goes to 1.
Yeah, you're waiting for some other thread to signal you, and it doesn't matter that the other thread never needed to wait for that permit necessarily, right? It's just a way to say, hey, let some other thread signal me. Is that what you're going to say as well? Yeah, there you go. Okay, so that's what it is here. We don't have any permits necessarily. Okay, the permit wait means you just have to wait for a signal, which can come from any other thread. I'm going to show you an example of where this is another case of this where it's actually more interesting. Yeah, Bernard.
Explain again how, so like anyone can send this signal?
Yeah, any thread can say permits.signal. Okay, it doesn't matter that it didn't have any lock to begin with. It might be that your logic says, hey, this one thread needs to wait for something. In fact, I'm going to show you an example in a second where it actually is useful. But it might say this thread needs to wait for a whole bunch of other stuff to happen, and one of them is going to signal it when it finishes. And it just waits. It doesn't have a permit necessarily. It doesn't need to lock anything until it just needs to get the signal is really what it needs to do. Okay, I'll see that in a second. But my next question is, what if you then said permits negative number? What does that mean? Let's look at the code too. What were you going to say? Yeah.
That many programs need to signal before anything can be.
Yeah, that's exactly right. That many different threads need to signal before it can actually do anything. Let's just go look at the actual code for semaphore. Okay, I gotta remember where it is. Let's see, /user/class CS110. I think it's local source, I believe, and then threads. There it is. Okay, semaphore.cc, and you can all go look at this. Okay, let's look at how this actually works. By the way, it's got a CV in there. It's got a conditional variable because that's how we built it, right? Let's look at the wait and the signal. Okay, wait does the following. Okay, wait has this mutex that it actually tries to acquire because it does need to update that value. Okay, so you have to have that lock in there in some sense. Okay, then it does a CV wait, and it does basically wait until the value is greater than 0. Okay, and then it decrements the value once it actually acquires that lock. Okay, that's what wait does. What does signal do? Well, signal acquires the lock, okay, and then increments the value. And then if the value becomes 1, it notifies everyone. Okay? Yeah.
Is the mutex m a global variable? Or where is that?
Mutex m is a class variable. Yep. It's a class. If you look at, let's see if I can do this. Actually, we'll do it here. Let's see. It's there. Include semaphore.h. There we go. It is there it is. It's a class variable, right? So when you create the class, now you've got the mutex in there, so it's shared between the functions. Okay. All right. So that's how signal and wait work. Well, notice that if the it's really only either incrementing or decrementing that value. So if you start that value off at some negative number, well, it's going to take that number, kind of -1, number of signals or rather +1, that number of signals to get up to 1 to actually notify the waiting threads that it's actually been done. Okay. So what is an example of when you might need this? Well, what if we did the following? Okay. Let's say we had a program where we had 10 threads we're creating, and they each need to do something, and then one more thread needs to wait for it to actually proceed with its thing. Now, you could do something like join all the 10 other threads and then do the next thing if you wanted to, but maybe you want to keep those threads going. Maybe you want to do other logic that's going to eventually do something else in those threads or something like that. So what you can do in this case is you can say, let's actually go and create these threads, and then each thread does its thing. In this case, it's just going to do a cout, and then it's going to send a signal on that semaphore. And each thread has no idea which number it's incrementing. It just goes, look, I'm done with my stuff. I'm signaling. Anybody who cares, I'm done. And it signals it, right? And then the read after 10 function here, well, it just waits. And because we started out this semaphore at, in this case, -9, okay, once there's 10 things that happen, it gets incremented to 1, and that's when the wait happens, and that's when the actual semaphore will allow the lock to continue. By the way, bringing it back down to 0, as it turns out. But that's a way to do a signal like that through a thread that makes it so that you can do 10 things in a row, and the last one gets to work last like that. So let's try this. Let's see. Live lecture, threads, CPP. I think it is negative semaphore. Okay, so let's look at negative semaphore, which should be exactly what I just said. It is. And there's where we're creating the semaphore, -9. Okay, and then passing that semaphore as reference into all the 11 threads we happen to have. And negative semaphore, there we go. So the threads, they all did it in their own order, which they're going to. Each one signaled after it got done. And then when the last one received all those signals, it proceeded. And that's how it worked. Okay. So questions on the new kind of way we might use signaling? We're going to see an example in a second, a bigger example in a minute. Got that? All right, 3 different types: mutex, conditional variable any, semaphore. We will use conditional variable any less frequently because we've got semaphore. You will still use mutexes a lot. So you use those two much more than conditional variable any on its own, although you may have a reason to use that at some point. Okay, let us talk about another pattern here. So here's a pattern that's going to come up occasionally. And this is going to leverage the fact that we can use like 0, not necessarily negative, but we can use 0 for our semaphore to go, okay? It also can be kind of a way to not have to use thread join until you absolutely need to, okay? So here's what we're going to do. We're going to look at a program that has 2 threads that are both acting on a particular data structure. One of the threads is writing things to it. The other thread is going to read from it, okay? And it's in fact going to read the data that was just written, okay? This is very similar to a pipe, okay? In fact, pipes may use some of this kind of under the hood as well. But it's very similar to the idea of you're writing some data and another one's reading the data from that data structure, okay? It's kind of like a web server and a client, where the client to the web server, like you typing in www.google.com, that request goes out to the Google server and Google gives you back the data. There's kind of a handshake there where you're requesting something and then the data has to come back. It's kind of like that, and we will do more of that. If we get time today, we'll see another example of that as well. And as I said, it's kind of like a pipe. Okay. Here's the initial program that I will zoom up and we'll look at in a little bit of detail. Okay, how many people remember, well, you remember queues from CS106B. Did you ever talk about like a circular queue or a circular buffer? Remember those? Okay, well, some people do. And if you took 107E, you definitely know those because I know it's part of the assignments. Here's what a circular buffer is. Let me actually unzoom and draw a little bit here, if I can. Hey, look at that. It's the one from last time. Okay, cleared. Okay, my horrible drawing skills will come back again. Okay, so a circular buffer is simply like this. You can model it like this anyway. You can think of it as a circle if you want to. But a circular buffer is like, if you start writing here, the next place you're going to write is here, then here, then here, then here, then here, then here, and then you just wrap around and continue to write here. So you need a head and a tail, more or less, okay? In fact, you can keep track of that in your program with just a mod operator to keep track of where in the actual circular buffer is. So you can have the buffer partially filled or whatever. The next place you write is here, and let's say that one's filled, that one's filled, that one's filled, that one's filled. I guess if your next one you're writing is here, this one's not filled yet, and so forth. But the idea is, let me erase that like this. So let's say that everybody else up to here, let's say it was like this, was filled. Let's say that was filled, and we're about to write here. We would then fill this one. Oops. We would then fill this one, and then come over here, and this would be the next one. Then we'd fill this one, and then the next one would be filled with over here, and so forth. If you ever get to the end where it's completely filled, you should not continue to write to it because it's full. That's a circular buffer, and it makes it nice instead of having to like create nodes at each time and like walk through them one at a time. You can just have one array and go through it in a circular way. Okay. Anyway, that's what a circular buffer is. So what we're going to do is we're going to write a little program, or look at a little program that has this circular buffer where one of the threads is going to be doing the writing and the other thread is going to be doing the reading. And it's going to hopefully keep track of who's writing where such that and reading so that it doesn't ever trample on the other one or read data that might not be available yet. Okay? So what does that mean in terms of this program? Well, let's just look at how the program is implemented so far. Okay? We have a writer, which basically is going to write random characters. It's going to randomly have a character, and it's going to put that character into the buffer, one after the other, and it's only a buffer with 8 positions in it, but we're going to do this 320 times. Okay, so it's going to write, and then wrap around, and wrap around. Now, if everything went well, the reading and writing would happen at the exact same rate, so that you could do that, and then the writer might be a little bit ahead of the reader, and they would keep going in that circular pattern. That would be ideal. Okay, but it's a very simple thing that's happening here. It's just taking that random character, putting it somewhere in the buffer, and then when the I variable gets bigger than 7, it wraps back around to the beginning and keeps going. And it just does that 320 times, putting the data in there. Okay, that's what it does. And then when it's done, it says, each time it says that it's put that data in there. Okay, the reader does the reverse. It goes through and it reads the data one character at a time and then just wraps around and keeps reading data. Okay, so in a perfect world, the writer might be 1 or 2 steps ahead of the reader, and everything would work perfectly. Okay, and these are in different threads, so you might think, oh, there's a race condition here. Ah, there is. Let's actually look at it here. Okay, this is called confused reader-writer. Okay, and remember, it's taking random characters and then writing them and then reading those random characters out. So it's going to look a little funny here at first. I will actually stop it because it's doing that. But let's look at what's happening here. Okay, so the writer is ready to write, and the reader is ready to read, and the writer publishes S. Okay, well the reader consumes space. Well, what's going on with that? And then it says the reader consumed G, and then the writer wrote in J, and the reader consumed at. Well, what's happening here is the reader is trying to read before the writer has ever even written anything, and whatever the garbage was in there to begin with is what gets read out. Okay, and so eventually, and then it reads consume data with nothing and blah, blah, blah. I can't even write it. Eventually, you might see some of the data getting in there, but it's all garbled, and and the writer is writing over parts, and it's not working the way we want it to. Yeah.
Are they writing to and reading from the same file?
They're writing to and reading from the same buffer, which is just a char star buffer. Called it, yeah.
So you don't have to worry about cursor being.
You don't have to worry about any. Well, that's a good question. You said you don't have to worry about any cursor. We kind of are worrying about the cursor, right? Let me go back to the drawing again. Okay, let me actually redo the drawing like this. Okay, here is the buffer. Okay, let's do it in a little more even. Let's say there's 1, 2, 3, 4, 5. Let's only say there's 6 places. Okay, let's say that this is where the first read is going to happen, but it's also where the first write is going to happen. Okay, so let's call this the read head and the write head there. Okay, well, where is the last thing that could possibly get read? It turns out it's this as well, like if you wrap all the way around, but that's kind of a nuance. But for now, let's think about it. Let's say that the reader tries to read first. Well, it's going to read garbage here, right? So that's going to be garbage if it gets ahead. Well, let's say the writer did get to write A. Okay, the writer writes A, and then the writer writes B, and then the writer writes C and D. And let's say the reader is nice and starts reading now. Well, the reader will read A and then be here, and the reader will read B and be there, and then be there, and the reader will read D, etc. And let's say E, F, and then it comes around here and reads G. Well, good. Let's say the reader, for some reason, stalls reading right here. Well, this is G, and then this is going to be H, and then this is going to be I. It's going to be J before the reader ever reads it. So that's the big issue here. Okay, if they're not in perfect sync, they're going to be in trouble. Okay, now the perfect sync is actually a little bit nuanced as well. To be perfectly synced, how many things can get read before anything's written? 0, right? You have to write something before you can read any of it. How many things can be written before something must be read? The max number of things, right? So you could write all the way to the end here before going back, but the instant you go back, if nothing's been read yet, you had better wait. Okay, so that's going to be the idea of what we're going to do with this program here. Okay, so anyway, we go back and we look at it again, and we go, it's completely garbled. Nobody's in the right order. It should have read SJCMN. Let's see, there's an SJCMN. It did read it starting down there. But eventually, they're just not necessarily in sync. And a bunch of stuff got read first and whatever. All right. Not so good. Okay. How can we fix this? Well, there are different ways of fixing it. Okay, you probably could use a couple of mutexes maybe if you wanted to and try to set it up like that. That's one way of doing it. The way I want to show you is by using 2 semaphores. Okay? What we're going to do is this is actually kind of what we just went through, why it's broken. There's nothing that tells the reader that a slot can be read from yet, and there's nothing to tell the writer that all the slots are full. That's the big problem. Okay? All right. So what can we do? Well, we can have two semaphores. Okay? If we have an 8-character buffer, we can initialize an empty buffers to 8. In other words, it starts out with 8 empty buffers. There's 8 spots that are empty. So far, so good? Okay. And then we can also set up a semaphore that says full buffers. Well, how many are full initially? 0. So let's do a semaphore starting at 0, which is that weird case where it's always going to require a signal to at least get going, because it started with no permits available, and that's what's happening there. Okay? So we can do that. We can set up the semaphore full buffers and empty buffers. The full buffers, if you say a semaphore with no parameter, it starts out at 0. Okay? If you do an empty buffer, if you do the parameter in here, that's how many permits there basically are, and this one says there's 8 empty buffers. Then you have to, of course, pass both the full and empty into both the reader and the writer, because they're both going to be handling both reader and writer. One's going to be waiting and then signaling the other, and the other's going to be waiting on the other one and signaling the first one. So that's what we're going to have to be working on. Let's see how this works in the actual functions. So what do we have? All right, we've got the full and the empty semaphores here. Okay, we are still going to do the same logic as before. We're just going to do the for loop through the entire buffer. The first thing the writer is going to do is it's going to wait on the empty buffers. But we initialize those to 8. And for a semaphore, if the count is 8 permits, will it wait at all? No. It says, great, I can start writing. And so boom, it starts writing, and then it tries to wait again, and now there's 7 available, and boom, it starts writing, and that's that. And it will keep going. Okay? After it writes a character, it signals the full, hey, there's a character I just wrote. And so that increments the full counter in the semaphore to 1, and it signals, because it incremented to 1, and it signals the other thread, the reader, hey, there's something available, I just put something there. Okay. All right, let's look at the reader. The reader does kind of the opposite. It still goes through the loop and does it. It starts by waiting for full. Well, nothing's full at the beginning, so reader has to wait at least one iteration of the writer putting something in there, because the semaphore it's using starts out at 0. Okay? But then it immediately gets a signal once the first thing goes into the writer, or once the writer writes 1, it immediately gets a signal and can read it immediately. It might be just one step behind, because maybe the writer hasn't written the next one yet. And then it does have to wait again. But it will do it immediately when there is a spot available. And there may be many, depending on how many the writer wrote in. There might be many in there, up to 8. Okay? And then, let's see. It signals empty, saying, hey, I just emptied 1. And that's when the empty, which the writer, when it's waiting, could end up going forward. Okay? So this one, by the way, will do this up to 8 times without the reader doing anything. And we can test that as we go. And then it should work. So this is now how the semaphores are going to be useful to us to keep everything in order. Okay, let's actually look at that one. This one is just called reader-writer, the correct one. So I'll let that go in there for a bit. And let me just zoom up to the top here. Okay, the writer's ready to write and the reader's ready to read. Great. The writer published A. Well, guess what? The reader immediately consumed A. And there's, by the way, I should have said this before. There's a little bit of random sleeping going on here too, so that this is why it isn't just one after the other, because there's some random sleeping going on here. The reader got A in order, and then Y goes in, and then Y comes out, and then W, I, Q, W. Well, it must have been that the reader went to sleep for a while, because the writer got a chance to put 4 new things into the reader, W, I, Q, W. But what gets read out? Oh, good, W, I, Q, W gets read out. So we know it's going to be in order there. Okay, and then it continues going through here. I'm not sure we might get to a point where 8 things go in and it waits that long, but we can do that. But anyway, it is definitely going to do it in order. Okay, that makes sense to everybody why that's the case? If it doesn't, go back and look at the code again, and remember, go look at the semaphore code and see how that actually works as well. Okay. All right, let's look at the code. Yeah, Eva.
Does it matter if you join the writer first or the reader first?
Does it matter if you join the reader or writer first?
The friends, yeah. Like, because we're waiting for the friends to finish. Does it matter which one we call it join functions? Because we're waiting.
Yeah, good question. Does it matter if you, let's actually look at the actual code here, because I didn't put that in the one main again down here. Does it matter which one you join first? I don't believe it does. Why? Because as long as they all get to finish, then the buffers will be filled in that case, right? If you try to, actually, let's see. If you try to wait on the reader first, it might get that the writer ends up, let's see, if you tried to wait on the reader first, it might be that you have to do it in order just because you have to write before you can read, and if you wait on the, let's see, if you waited on the reader first, you might end up not being able to read at all, and therefore, I'd have to think about it more. Yeah, I'd have to think about it more, but I don't think it's actually a race condition in that case. The final waiting, it might be. I'll get back to you on that. Yeah, good question. Yeah.
We try it.
Yeah, so, I mean, we can try it. I don't know. That's a good. We can absolutely try it, but I don't know that it's going to prove our case. It'll prove the negative, but let's try it. Reader, writer. Okay, and then reader, writer. There we go. Okay, let's just see if it goes all the way through. It would only happen near the end. We would care because one would end before the other. But no, again, now that I think about it, I don't think it's possible for if one ends and it's waiting for the other. Who cares? If it's waiting for the first one and it hasn't ended yet, who cares? So, or if the data hasn't come, the other one wouldn't have ended yet. So I think it doesn't matter. I'm pretty sure. I'll confirm that, but it did finish, so at least we know that it can work. But again, these sorts of things don't do that. Let's do this though. Let's put in just a little bit more waiting. We'll put in. Let's see. Let's put a little sleep for in here for like 3 seconds, right? Before it even starts to try to read. This is going to mean that the writer is going to put 8 things in there, and then hopefully it will wait. Let's see if that works. All right. Reader, writer. Okay, there we go. So it's put 1, 2, 3, 4, 5, 6, 7, 8 things in there, and then it went going after the reader finally woke up. Now I'm going to start reading some things. That's how that worked. Okay. And the other way around, if we put it in the writer, if we put it in before the writer, what's going to happen here? What do you think? If I put the sleep there, what's going to happen now? Yeah, what do you think, dude? It should wait 3 seconds before doing almost anything, right? Because I think that's a good answer. Make reader writer, and then we're going to. There we go. Okay, there. Everybody's ready. Then finally, the writer starts writing after 3 seconds, and then boom, it goes. Okay, because nothing's ever been written, the reader can't bother to or can't do the reading yet. Question.
I have a question. So usually at the end, maybe it'll happen here too. It prints out like 9 reader consumed. So what's going on with that? Like, how does it get 9 there?
Good question. How does it get 9 there? Let's actually run it in this case and see what happens if we get a whole bunch. Did it do 9, or it might just be probably just a race condition with who's writing and reading. That's my guess. It can't read 9 without 9. It can't read 9 in a row because there aren't 9 spots, right? But it's probably the last write, the read's already printing out or isn't printing out yet or something like that. So it's just a race condition there. If it were like 20, I'd be a little suspect. But I think 8 or 9 or 10, not a bit. 1, 2, 3, 4, 5, 7, 8, 9. Yeah, last one. And it did do 2 S's at the end, so that wasn't a weird. Yeah. So yeah, I think it's just that it's probably just a race condition there. It's also that maybe the writer's got a little more, is writing a little faster than the reader anyway, and the reader just never quite catches up until the last part where it goes, finally I can read all the rest of the data. Yeah, I think that's what's going on there too. Do you have more questions? No, are you sure? Okay. Anybody else? All right. So that's that reader-writer paradigm. As we go. Okay. All right. I think we have time to take a look. We may not get through the whole thing, but let's take a look at this thing called Mythbuster. Okay, this is a Jerry Kane special. It's called Mythbuster because all it does is it basically, do you ever log on to a myth and you go, wow, there's 1,000 other people on here and it's really slow and it's kind of annoying, and maybe it'd be kind of nice to know which myth has the least number of like CS110 people slamming it. Okay, well that's what this Mythbuster does. Okay, it basically goes to all, I guess, 10 or 12 myth machines, and it queries them using a kind of a wonky hack to actually see how many threads for people in this class are using that. Now, I also think it should check 107, or just in threads in general, but whatever, it checks this class. Okay, and I'll show you it running before we do anything else. Okay, Mythbuster, let's do it concurrent. That's the one we don't love, but okay. Okay, so holy smokes, who's using all these processes? What is this? Machine, and there's a little race condition there anyway, with the number of least, machine least loaded by CS, machine number of processes on least loaded machine 74. So if you were to use it, you would want to log on to Myth 52, but I'm actually really curious. Myth 65, SSH, Myth 65, Myth 65, H top. Let's see. Okay, let's see. So there's that. Let's see. Factor, Python factor. Who is this? Emma, is Emma here? It's Emma. Okay, so you left a whole bunch of factors like going in your program. Possibly when you started. I don't mean to call Emma out, but she's after me. Look, there were thousands of them, so Emma's not alone. I guarantee you that. There's some more. Okay, there's some more. All right, let's see if we can find a bunch more. Yeah, there's a whole bunch more. So you should kill all your processes. So I literally, when I ran this earlier, I noticed some of these, and I'm gonna have to write a little note to next quarter, make it so that every time you submit, it just kills all your outstanding processes that are still running on whatever myth one you have, because that's it. So then anyway, you guys are all doing that, and those poor 107 students can't use the myth machines because neither can you. So. Emma, what you can do, by the way, is you can say, I think, kill all Python, and it will kill all your Python things on that myth machine, I believe. You can try that and see if it works. And maybe it will do that. And if we're all nice, we can do that. The good news, by the way, is that all of these processes, while they are taking up memory, they should all have T under the status, which actually means stopped. So they're not actually spinning, which is good. So thank you for not like running spinning ones. But yeah, they're generally not good to like have them sitting there doing nothing until the machine reboots. That's kind of what's going to happen. So anyway, that's what Mythbuster does. And Mythbuster runs somewhat slowly in that it has to pull that was the concurrent ones. This is the fast one. The sequential one's the one that's going to be slowly. That was a nice fast one. The sequential one is going to be slowly because it has to do each one in order, and it's just got to go and do this querying thing. Some of the myth machines, by the way, are down or like not available for SSHing into for whatever reason, and it has a 2-second timeout on that, so it has to wait for that. Okay, so what does this mean? Well, the concurrent one, which was much faster, did it in threads. Okay, it just said, I'm going to have a different thread asking this myth machine how many threads it has or how many processes it is, and if it takes a little while, great, some other ones are still going to be running. You'll notice it's out of order. We could figure out how to order it a little bit better, but you have 56, 52, 58, etc. This one at least is in order, and some are missing because it's not, they're not, like myth 57 is down or whatever, but maybe it should just say myth 57 is down. But the point is that you do it concurrently, it's slow. Once you have threading, you can wait for all those servers to reply to you, or if they're broken down, you can do that. So let's take a look at some of the code for this. Okay, here's the various data structures we're going to have. I happen to have made a list of all the student SUNETs in the class. Okay, and that's what it's asking for. So it reads that file, and then it checks each myth machine against all those names. Okay, it just looks for the process numbers. Okay, it has a set of all this. That's a set. It reads that you can read the student files. It's got a map that counts the processes for each myth to how many processes it has. Okay, compile the process count map is going to pass in those two details, and in there we're going to do all the threading, and then it's going to publish the least loaded data. So that's how the program is going to work. Okay, let's see how, I already mentioned all these things, went over those things. Let's see, anything important there that we need to know? Nope, I think we talked about it all. The details are in a the get num processes. Okay, this is where it actually goes and gets for like myth 54, it gets the processes and then it checks them all against the students in the class based on their username. Okay, and this is how it would work in the sequential version. Okay, it's pretty straightforward. Basically goes through each myth, okay, from 51 to 56, and then it counts the number of processes in each one by calling this get num processes. Well, that's the slow part, because you've got 12 different processes, 10 different myths, and each one could be stalling. Okay, so that's what we're going to have to try to avoid. This is what I showed you it working already. Okay. The point is that each call spends most of its time waiting around for the myth machine to respond to it. Whenever you log on a myth and you're waiting, well, that's what your program has to do too, right? It can't go on to anything else if you do it sequentially. So that's the big deal. Okay. So when you're counting these, what you want to do instead is do it in threads. Okay. So let's see how this might work. Well, we're going to have a count CS110 processes again. We're still going to pass in the num. We're still going to pass in the set of students. And we're still going to pass in the process count map. And this time we're going to pass it in and not just give the return value. And then we're going to have a mutex to lock on the process count map. Why? Because you don't want different threads trying to update the map at the same time. Okay? You might think, well, why does it matter if two threads with two different myths updates the map at the same time? Well, do you remember how maps are built under the hood back to CS110 or 106B days? Remember how maps are generally, some like maps are generally built? If it's a regular old map, you know how it's built, yeah. A tree, yeah. And if you have a tree and if it's a balanced tree, well, that means that you have to actually move nodes around when you're inserting, and that would be bad if two things tried to insert at the same time. They'd be moving things around and it would go haywire. An unordered set is using a hash table, which also might cause similar issues, especially if you have hash collisions and so forth. So either way, you don't want two threads to try to write to that map at the same time, so you lock around the map, but the map writing is very quick. Writing to the map or reading from it, very, very quick. Okay, so we can not worry too much about that. Okay, in fact, we're just going to do a lock guard around it. Okay, we are going to change the we are going to, let's see, we're going to do the actual count process or get num processes in here. Once we get the number of processes, we are going to, if the count is greater than 0, we're going to update the myth count number and put it in the map. And that's a very short, this whole section here is very short to update the map. This is the part that takes a long time. If you're trying to wait, that's the part that takes a long time, but if you're doing it in 12 different threads to 12 different myth machines, it's actually fine. Okay? But you have to lock around updating that map for everybody. Okay? And then we have permits in here. This is so that we don't slam all the myths at once, I guess. It's not a big deal for 12 different myths, having 12 different threads. But in this case, how many did we set up here? Did we say how many we set up? Oh, I guess we're gonna see how many. Oh, here we go, 8. So we're gonna say we're only gonna allow 8 threads to go at a time. Why? That's just kind of nice when you're doing networking things to limit it to some reasonable amount. But we could get away with thousands if we really wanted to in this case. But there's only 12 myths or something, so that's that. Okay, and then we signal on the end there. Let's see, when do we actually get the permits? I don't see a permit's weight in there, so.
It's in the for loop on the bottom, for num k.
Oh, it's down here. Let's see. Oh, right. Okay. When we're actually setting up the threads, that's when we're doing it. We will see a different model next week for a different model. For this, in this case, this is when we're setting up the threads down here. Okay. So how are we doing that? We're saying 8 permits, and we are going through. And if we're only going to launch 8 threads at a time. When one of those threads finishes, it will signal this to start the next thread. We are not joining on any threads until all the way at the end. Okay, those threads will end, but we're only allowing 8 to kind of go at the same time. At some point, there will probably be 9 threads going at this time because the signal is going to happen and another thread's going to get spun up and then this one's going to close. So in this case, we could have an off by 1, but it doesn't matter. But now there's 9 threads instead of just 8. Yeah, question?
Sorry, I may have missed this, but I didn't know signal between elements is on right exit.
Oh, sorry. Yeah, I didn't tell you about that one. So in this case, I guess there wouldn't be. It probably does it after the thread, just as the thread ends. The semaphore allows you to say on thread exit, do the actual semaphore releasing. I don't know the magic that has to go into that. We could probably look it up in the actual. Let's go look it up real quick. But yes, if you want the signal to happen after the thread is when the thread is closing down. That's what you would use for it. Good answer on or good question on that. User class CS110 local source threads semaphore.cc. Okay, let's look for on thread exit. Okay, here we go. Let's see. Yeah, so it looks like there needs to be some p thread magic going on there to basically say, hey, do this when the thread's exiting, and you can do that. So it's a little bit of under the hood magic happening there with leveraging that we're using threads to do all this. Yeah, you do not need to know that for anything specifically. Just know that if you want to exit the thread, or if you want to send that signal as the thread's shutting down, that's when to do it. Good question.
But that thread won't shut down until join?
The question is that thread won't shut down until join. It will shut down. It won't get cleaned up until join. So in other words, it still stops, and it's no longer taking up any cycles on the processor. It's just waiting. The operating system or the thread manager is waiting to clean it up until you join it. Yeah. Other questions on this? All right, let's see. Let's see. Polling the myths concurrently. Well, what does that do for us? That allows us to wait on the dumb, slow network or the connection to happen. Okay, because we've got lots of them happening. Your computer has the ability to send lots of messages to different machines all at once. That's fine. It's got its own waiting and de-interleaving happening with that. But as far as you're concerned, your program can send as many messages as it wants to different servers, in this case all the different myths, at the same time through various threads. Okay, the semaphore limits the number of threads, and yeah, here's the on-thread exit that we talked about. It's an overloaded version of signal. It schedules after the entire thread is exited, so that makes it so there's not 9 threads at once going, although maybe for a very short amount of time, but not long anyway. And that's it. And you can see the concurrent one versus, let's do this. Let's do it in 2 different windows. So let's do it this way, and all right, so I guess it's a little, it's interesting that I'm running this on the myths and checking all the myths, so it's a little, okay, I think we can do it this way. Here's what I'll do. Let's do, I want to make this window a little smaller, and okay, so we're going to run mythbuster. Let's do the sequential on this side, and then let's see, live threads. Reds CPP. Let's do the mythbuster concurrent on this side. Now I'll try to hit return and then really quickly hit the other one. We could time that if we wanted to, but I said, okay, ready, boom, boom. Okay, and the mythbuster sequential one is still going while the other one's already done. All right, did it all in the threads all at once. The other one is still one after the other, after the other, after the other. All right, what questions do you have about this stuff? You see how this threading, you're going to have to think about race conditions a lot, but there's lots of cool models that we can do. Next week this week and then next week we're going to talk about some other cool problems where we're modeling bigger ideas. In particular, one is an ice cream shop, kind of fun, that we're going to model that allows you to do threads that are waiting on other threads and using this whole idea of permits and so forth. Question?
When you don't specify a myth machine, does it give you the least common?
If you don't specify a myth, it checks all of them in this case.
Like when we're SSH.
Oh, if you just, yeah. Oh, good question. If you, this is just about logging on to the myths in general. If you just say SSH myth, it will pick one. There is a load balancer that's doing exactly what our program just did, kind of. Basically says, oh, who's busy right now? Now, I think it's kind of continually looking at who's busy. It's kind of got connections that are open all the time, going who's busy, and it tries to send you to the one that's least busy, right? It can't figure out if Emma's got all those processes stopped, though, so sometimes it doesn't work. No, it definitely, it's doing the exact same thing. It's really doing more or less the same thing for you. Yeah, good question. All right, any other questions? I think we'll get out of here a couple minutes early. All right, we'll see you Wednesday.